Introduction. Son, put all the items on the counter table for billing.
Yes, Father. Father, I want to ask you something.
Yes, son, you can ask.
Father, the shopkeeper using some light device to access the details of all the goods. What is it and how it works?
Son, it is a barcode scanner and works on the principle of photodiode. A light source emits the light on the object and reflected light sends by photodiode and produce electrical signals accordingly. It is an application of semiconductor electronics.
Okay, Father. I got the answer of my question and I want to know something more about the semiconductor devices.
Students, today we will study more about the semiconductor electronics. Objectives. At the end of this lesson, you will be able to describe optoelectronic junction devices, know photodiode, understand light-emitting diode, describe solar cell, define junction transistor, analyze common emitter transistor, explain transistor as an amplifier, explain transistor as an oscillator, describe logic gates, define integrated circuits. Optoelectronic junction devices. The semiconductor diodes in which carriers are generated by photons are called optoelectronic devices. Optical semiconductor devices are widely used in fields ranging from optical fiber communication systems to consumer electronics and have become indispensable devices in the equipment and systems making up the infrastructure of our society. The three important optoelectronic devices are photodiode, light-emitting diode, and solar cell. Photodiode. A photodiode is a receiver for optical signals. It is a reverse-biased p-n junction which is designed that light falling on it may enter into the charge-depleted region of the junction. When diode is in dark, a small current known as reverse saturation current or leakage current flows in the circuit. This current is due to the drifts of electron-hole pairs which are thermally generated in the charge-depleted region. This leakage current increases with the rise in the temperature. The leakage current also increases with the increase in the level of illumination. This is because more intense light would produce more number of electron-hole pairs due to increased number of photons. The photodiode quickly responds to light without any delay. It is used for detection of visible and invisible optical signals. It is used in optical communication, optical switching and character recognition. Light-emitting diode. It is a semiconducting junction diode which emits light when a current is passed through it in the forward-biased condition. It is a p-n junction made of gallium arsenide, GaAs, or some other suitable semiconducting material. The p layer is made thin so that light energy may reach the charge-depleted region after traveling a very short distance. When a forward bias is applied to a p-n junction, the barrier height decreases and with enough forward bias, the charge-depleted layer practically disappears. Under forward bias condition, when a current flows through a p-n junction, then several pairs of electron holes recombine and each recombination gives rise to a photon. The frequency of light so emitted depends on the energy released, which in turn depends on the band gap. The intensity of light emitted depends on the number of photons, which in turn depends on the number of recombination taking place. LEDs are available to emit light of all colors. LED requires small voltage and power for their operation. They are used in optical communication devices, TV remotes, and numerical displays in calculators. Solar cell. A solar cell basically converts solar energy into electrical energy. Light energy is made to fall on a metal surface to liberate out electrons from metal, provided the energy of a photon is greater than or equal to the work function of the metal. A p-n junction diode can also give out emission of electrons and holes by absorbing solar energy. The p material at top is very thin compared to thickness of n material. Thus, solar energy photons entering from top glass window easily penetrate up to both sides of junction. As the photons collide with valence electrons of both p and n materials, they impart them sufficient energy so as to leave their parent atoms. Thus, a good number of electron-hole pairs are generated on both sides of junction. Hence, a potential difference is created between anode and cathode. This potential difference can give a current flow through an external load resistance. Junction transistor. A junction transistor is an extended form of junction diode in which there are two junctions between three chips. There are two kinds of transistors are NPN transistor, PNP transistor. NPN transistor, one P material being sandwiched between two N materials. This device is called NPN transistor. PNP transistor, one N material being sandwiched between two P materials. This device is called PNP transistor. The flow of current takes place due to movement of electrons and holes both. Thus, these are called bipolar junction transistors. Components of bipolar junction transistor. Total material is divided into three parts by two junction layers in between are emitter. The first chip of transistor is the emitter, which is heavily doped extrinsic semiconductor. It is heavily doped as it bears the responsibility of supplying the mobile charge carriers to the next chip. Base. This is the middle chip of transistor, which is very lightly doped. The thickness of this part is extremely small compared to the two side chips. Collector. This is the last chip of the transistor which bears the responsibility of collecting the mobile charge carriers coming from base and supply large power to the load. This chip is the thickest one among all three. It is a moderately doped chip. Transistor biasing. In the normal operation of transistor, the majority charges in heavily doped emitter are to be transferred to base region and then from base they have to be transferred to collector region. For transition from emitter to base, the first junction between them has to be forward biased. As the majority charges of emitter reach the base region, they can be attracted towards the collector region only if the collector end is reverse biased. Terminal currents of transistor. We consider PNP transistor to understand about different terminal currents. Emitter current, IE. With forward biasing at the first junction, the majority charges of P emitter move from emitter to base, constituting a current called the emitter current. Base current, IB. As the holes reach the base region, most of them are transferred to collector. The small number of holes drifting out from base constitutes a current called base current. Collector current, IC. Most of the holes that go from base to collector form a current called collector current. IE is equal to IB plus IC. The current concepts are all same in PNP and NPN, except the fact that all currents are directed opposite in the two cases. Common emitter transistor input characteristics. In a common emitter configuration, the common or ground side of each voltage source is connected to the emitter. Input characteristics. The variation of base current IB with base emitter voltage VBE at constant collector emitter voltage VCE is called the input characteristic of the transistor. For VCE is equal to 0, the input characteristic is essentially that of a forward biased diode. Increasing VCE with constant VBE effectively means an increase in VCB. This causes a decrease in the effective base width and results in a decreasing recombination base current. For SI transistor, VBE is about 0.7 volt. VCE must be sufficiently larger than 0.7 volt so that the magnitude of the reverse bias voltage VCB across the base collector junction remains high. Input resistance. This is defined as the ratio of change in base emitter voltage to the resulting change in the base current at constant collector emitter voltage. Common emitter transistor output characteristics. Output characteristics. The variation of collector current IC with collector emitter voltage VCE at constant base current IB is called the output characteristic of the transistor. Saturation region. The part of the characteristic curve lying between origin and the knee of the curve is called the saturation region. In this region, both collector junction and emitter junction are forward biased. Active region. The horizontal part of the characteristic curve is called the active region. In this region, emitter junction is forward biased and collector junction is reverse biased. Cutoff region. In this region, both junctions are reverse biased and the transistor currents are negligibly small. A transistor operating as a switch in the off position is in cutoff mode. Output resistance. This is defined as the ratio of change in collector emitter voltage to the change in collector current at a constant base current. Current amplification factor. This is defined as the ratio of change in collector current to the change in base current for constant value of collector emitter voltage VCE when the transistor is in active state. Transistor as an amplifier. Amplification is the process of increasing the strength of a signal. An amplifier is the device that provides amplification without appreciably altering the original signal. We consider the operating point of the transistor somewhere in the middle of this active region. The DC voltage VCE is equal to VCC minus ICRC would also remain constant. The operating values of VCE and IB determine the operating point of the amplifier. If a small sinusoidal voltage is superposed on the DC base, then the base current will have sinusoidal variations superimposed on the value of IB. As a consequence, the collector current also will have sinusoidal variations superimposed on the value of IC, producing in turn corresponding change in the value of V0. VCC is equal to VCE plus ICRL. Nu I is equal to delta IB multiplied by RB plus RI. AC current gain is given by beta AC is equal to IC upon IB. The voltage gain of the amplifier is given by AV is equal to delta VCE upon R delta IB. Or it can be written as AV is equal to minus beta AC RL upon R. The negative sign represents that output voltage is opposite with phase with the input voltage. The power gain of the amplifier is given by AP is equal to product of beta AC and AV. Example. Let's take an example of transistor as an amplifier. The current gain for common emitter amplifier is 52. If the emitter current is 4 mA, find the base current and collector current. Let's see the solution. Given values are beta is equal to 52, IE is equal to 5 mA. We know that beta is equal to IC upon IB, which is equal to IE minus IB upon IB. On simplifying the expression we get IB is equal to IE upon 1 plus beta. Now putting the values in the expression and calculating, we get IB is equal to 0.08 mA. We know that IC is equal to IE minus IB. Now putting the values in the expression and calculating, we get IC is equal to 3.92 mA. Hence the value of base current is 0.08 mA and collector current is 3.92 mA. Transistor as an oscillator. An amplifier needs an AC input signal to produce an AC output signal. An oscillator converts DC into AC. Most oscillators are amplifiers with the following conditions. A positive feedback to the input must be given from the output. The amplifier gain must be greater than the loss in the feedback path. An oscillator circuit consisting of an amplifier circuit, tuned circuit in the collector, and an inductive coupling for feedback. The emitter junction is forward biased while the collector junction is reverse biased. The coils L1 and L2 are wound on the same core so that they are inductively coupled through their mutual inductance. On pressing the key, collector current suddenly starts flowing through L1. Consequently, a voltage is induced with coil L, which charges the capacitor C with such a polarity as to support the forward bias of base emitter circuit. On reaching saturation, collector current stops varying, hence induced EMF in coil L vanishes. The frequency of AC current so produced is given by the relation F is equal to 1 upon 2 pi multiplied by 1 upon under root LC. Logic gates. A signal which varies continuously with time is called an analog signal. A signal which has only two possible discrete values is called a digital signal. Such signals are conveniently represented by binary numbers which has only two digits, 0 and 1. Logic gates are digital circuits that follows certain logical relationships between the input and output voltages. The basic logic gates are OR, AND, NOT, NAND, NOR. Truth table. A table that shows all possible input combinations and the corresponding outputs for a logic gate is called truth table. Boolean expression. A shorthand method to describe the functioning of a logic gate in the form of an expression is known as Boolean expression. OR gate. An OR gate has two or more inputs with one output. The output Y is 1 when either input A or input B or both are 1. That is, if any of the input is high, the output is high. AND gate. An AND gate has two or more inputs and one output. The output Y of AND gate is 1 only when input A and input B are both 1. NOT gate. This is the most basic gate, with one input and one output. It produces a 1 output if the input is 0 and 0 output if the input is 1. That is, it produces an inverted version of the input at its output. It is also known as an inverter. NAND gate. This is an AND gate followed by a NOT gate. If inputs A and B are both 1, the output Y is not 1. NAND gates are also called universal gates because using these gates we can realize other basic gates like OR, AND, and NOT. NOR gate. It has two or more inputs and one output. A NOT operation applied after OR gate gives a NOT OR gate. Its output Y is 1 only when both inputs A and B are 0. Integrated circuits. An integrated circuit is a small electronic device made out of a semiconductor material. The first integrated circuit was developed in 1950s by Jack Kilby of Texas Instruments and Robert Noyce of Fairchild Semiconductor. Integrated circuits are used for a variety of devices, including microprocessors, audio and video equipment, and automobiles. Integrated circuits are often classified by the number of transistors and other electronic components they contain. SSI. Small scale integration. Up to 100 electronic components per chip. MSI. Medium scale integration. From 100 to 3000 electronic components per chip. LSI. Large-scale integration. From 3000 to 1 lakh electronic components per chip. VLSI. Very large-scale integration. From 1 lakh to 10 lakh electronic components per chip. ULSI. Ultra-large-scale integration. More than 1 million electronic components per chip. Assessment. Before proceeding further, let us know how much you have learned. Drag and drop the correct option. Did you know? LEDs are instant on, which means they achieve their optimal brightness immediately upon being powered on. The largest solar electric plants are located in Germany. They are the Bavaria Solar Park and the Arnstein Solar Electric Plant. The Arnstein plant delivers 12 megawatt of energy to about 3,500 households. Transistors have shrunk in size with a factor of 222 since the first Intel 4004 chip was introduced in 1971. Summary. Let us summarize what we have learned. The semiconductor diodes in which carriers are generated by photons are called optoelectronic devices. A photodiode is a receiver for optical signals. LED is a semiconducting junction diode which emits light when a current is passed through it in the forward biased condition. A solar cell basically converts solar energy into electrical energy. In a bipolar junction transistor, the flow of current takes place due to movement of electrons and holes both. Emitter is the first chip of transistor, which is heavily doped extrinsic semiconductor. Most of the holes that go from base to collector form a current called collector current. Logic gates are digital circuits that follow certain logical relationships between the input and output voltages. An integrated circuit is a small electronic device made out of a semiconductor material.